Hi everyone, today we're solving problem 25. In this problem, we're supposed to find the index of the first term in the Fibonacci sequence to contain 1,000 digits. Now, in the solution for this problem, it's a lot more mathematical than calculating out all the numbers in the Fibonacci sequence. We're not going to do that. We're going to jump directly to the first Fibonacci number to contain 1,000 digits. Now, how are we going to do this? Well, the mathematical formula we're going to create for this depends on knowing a few things. The first thing you need to know is Binet's formula. Binet's formula is an explicit formula used to find the nth term of the Fibonacci sequence, and it looks like this. And what this formula is going to let us do is it's going to let us jump directly to the nth Fibonacci number. And we can use this formula to create another formula that gives us the number of digits in the nth Fibonacci number directly. So let's go to our canvas. So here I've copied the formula from the AOPS website, and let's start. So before we create the formula to calculate the number of digits in the nth Fibonacci number, we first have to eliminate this term because the subtraction is going to make it harder to create that formula. So to see how we can remove this term, let's take a look at what the two terms in the subtraction are going to look like when n is high. So if we look at this is the golden ratio, 1 plus square root of 5 over 2. This is greater than 1. And if we have a base greater than 1 and we're raising it to a large power, we know that it's going to be really large. And in fact, we can state that the limit of this as n tends to infinity is infinity. But with this term, on the other hand, 1 minus square root 5 over 2, this is between negative 1 and 1. And taking a base between negative 1 and 1 and raising it to a large power will bring this power closer and closer to 0. We can say the limit of this as n tends to infinity is 0. And we know that n is going to be really large in the case that this produces a 1,000-digit number. So we can actually go ahead and cancel this out because it's going to be so small, and this is going to be contributing the largest to the actual Fibonacci number. Now let's rewrite this formula. So we now have the nth Fibonacci number is, and we can write this, 1 plus square root of 5 divided by 2 raised to the n divided by square root of 5. So now we have our formula for finding the nth Fibonacci number. Now next is creating a new formula based on this that gets us the number of digits in the nth Fibonacci number. So to see how we're going to do this, let's take a look at the log base 10 of a number and how that can be used to calculate the number of digits in any number. So the formula for finding the number of digits in a number n is the floor of log base 10 of n plus 1. And to see why this works, let's write out the first few powers of 10. So let's do 1, 10, and 100. So 1 is a one-digit number, and we know that this formula works because log base 10 of 1 is 0 plus 1 is 1. And we know that all of the numbers, since we're flooring this, we know that this 1 is going to be the same until we reach 10. When n reaches 10, this floor of log base 10 of n is going to jump to 1, and 1 plus 1 will be 2. And this 2 will continue till we get to 100. Now at 100, log base 10 of 100 is 2. 2 plus 1 is 3. And I think you can see where I'm going with this, because when we're at 1,000 then, we'll have 3 digits all the way up to 1,000 where we'll jump to 4. So at each power of 10, we increase the number of digits. Now all we have to do is take this formula and plug in f of n into this. So let's go ahead and write that out. So we'll get the formula floor of log base 10 of, now I can copy this formula here. So we'll have 1 plus square root of 5 divided by 2 raised to n divided by the square root of 5. And we'd have the floor of this, and then we add 1. Now we can go ahead and simplify this log a little bit. We know that if we have a log of a division, it's equivalent to the log of the numerator minus the log of the denominator. So you can go ahead and simplify this out. Log base 10 of, and now we copy our numerator, 1 plus square root of 5 divided by 2 raised to the nth power, and then minus log base 10 of the square root of 5. We floor this and we add 1. Now we can simplify this a little further. We know that if we're raising a power and then taking a log of that, we can just move the power out of the log. And we can actually do that to both of these because we know square root of 5 is the same as 5 raised to the half power. So you can do n log base 10 and 1 plus square root of 5 divided by 2 is phi, the golden ratio. So you can write phi right here and then subtract 1/2 log base 10 of 5 for this, and we add 1. So this is our formula for getting the number of digits in the nth Fibonacci. Now what we want to do is we want to find the first number that has 1,000 digits. So all we do is set this equal to 1,000. Now what I'm going to do is I'm going to take this and turn it into an inequality, getting rid of this floor. So first, moving the 1 here, this would become 999, and let's get rid of these floor symbols here. So then we'll have n log base 10 of phi minus 1/2 log base 10 of 5. And we know that if the floor of this is equal to 999, this must be greater than 999. And we want to find the first integer value of n that satisfies this. So we're gonna solve for n. So first we would move this over, so that would give us a plus 1/2 log base 10 of 5, and then we would divide it by this. So let's do that. I'm gonna write that actually over here. So we're taking this and we're gonna continue here. So we would have n would be greater than, starting to run out of space here on my pad to write, n equals 999 plus 1/2 log base 10 of 5, and this whole thing is going to be divided by this thing that we're dividing over. So this would be log base 10 of 5. And now if we want to find the integer value of n, the first integer value of n greater than this, we just know that n is equal to, and we can just move this over here. So pretend like it's there, and we do the ceiling of this. So you're just ceiling of this 999 plus 1 over 2 log base 10 of 5 divided by log base 10 of phi. So that's our formula. Now all we have to do is implement this. So I'm actually gonna I'm gonna switch over to IntelliJ. So let me find some empty space down here. So I'm just gonna quickly copy over the formula over here. So we have ceil, this is not actual code, but just so that I can remember before I clear this out. Ceil of 999 plus 1 over 2 times log base 10 of 5. Okay. Now that is divided by log base 10 of 5. Okay, now I can go ahead and clear this. Okay, let me go ahead and get rid of that. So I can pop it back at any time, but yeah, okay, cool. So that looks right. And now we need to actually implement this. So the first thing we need is this phi. So now that we're in Scala, and we can actually do a few cool things. Since we're dealing with a numerical constant, in our math we would draw it as this Greek symbol phi. And in Scala, because of support for Unicode, we can actually take Unicode phi, it's Greek small letter phi, let me scroll down, and we can copy this Unicode symbol and create a val phi. And this is going to be equal to, and phi is defined as 1 plus square root of phi divided by 2. So we do 1 plus math dot square root of 5 divided by 2. So now that we have this, now we just implement the rest. Val answer equals to math dot ceil of, and we have 999 plus, and now we do math dot log 10 of 5. We divide this by 2. Now in our denominator we just have math dot log base 10 of, and we can copy this Unicode symbol because I can't type it in, of phi. And now we can print ln our answer. Actually go ahead and get rid of this. Print ln answer. Now we can go ahead and run this. And we get our answer. So that's it for problem number 25. I'll see you next time when we solve problem number 26.